Welcome to the Explainer. Today, we're diving deep into the hidden science of polymers. These are the chemical giants that have, quite literally, built our modern world. From the clothes you're wearing right now to the tech you use every single day. So let me just start with a question for you. What on earth could a silkworm's cocoon possibly have in common with a modern nonstick pan? I know, it sounds like a riddle, right? One is this ancient, totally natural fiber, and the other is a product of some serious high-tech chemistry. But the answer connects them, and it lies in this incredible group of compounds that are at the very heart of, well, pretty much everything. To find that answer, we first have to understand a world that's built from molecular chains. And here it is, the hero of our story, the polymer. At its core, a polymer is just an unbelievably long molecule that's built like a chain. Just picture a massive molecular necklace. Now, the word might sound a little obscure, but you know them very, very well. Silk, the DNA in your own cells, rubber, and almost all plastics, they're all polymers. Okay, so if the polymer is the necklace, the monomer is the single bead on that string. These are the small, repeating molecules, the little building blocks that link together again and again and again to form that polymer chain. You could also think of them as molecular Lego bricks that build almost everything we see around us. So how exactly do these little monomer building blocks get put together to make these long chains? You know, the ones that make up everything from a plastic bottle to a synthetic jacket? Well, let's check out the playbook. What's so amazing here is just how elegant and simple this process is. It's called an addition reaction. You start with these simple little molecules, ethene. Then a chemical reaction comes along and breaks a key bond, which kind of frees up their hands, so to speak. Then they can all link together, hand in hand, forming this long, incredibly stable chain. And just like that, you've turned a simple gas into solid polyethene, the stuff that makes up plastic bags and bottles, and the single most common plastic on Earth. And this brings us right back to our opening question. You see, when a polymer is made from just one type of monomer, just one type of bead, it's called a homopolymer. But when you build a chain using two or more different kinds of monomers, you get a copolymer. And there's our answer. The Teflon on your nonstick pan is a simple homopolymer. But the silk from a cocoon, that's a complex, naturally occurring copolymer, two totally different materials built using the exact same playbook. Now, understanding this chemistry didn't just solve a few scientific puzzles. No way. It kicked off a synthetic revolution that completely, and I mean completely, reshaped society. This timeline really tells a story. We started out just trying to improve on nature. You see it right there in 1839 when Goodyear figured out how to make natural rubber stronger. But pretty soon, our ambitions got a lot bigger. By 1909, we create Bakelite, the first fully synthetic plastic, and it changed consumer goods forever. Then, in 1935, we invented nylon, a synthetic version of silk that turned out to be vital in wartime. But the story doesn't stop there, does it? The very success of these materials, their incredible durability, it created a problem that nobody ever saw coming, a legacy of waste, symbolized by the Great Pacific Garbage Patch. And so often, these world-changing inventions happen by complete accident. Take Teflon. In 1938, a chemist was just trying to make a new refrigerant. He went to check on a gas cylinder he thought was empty, but inside he found this really strange, slippery white powder. By all accounts, his experiment was a total failure. He hadn't made a refrigerant, he'd accidentally created one of the slickest, most nonstick materials known to science. And it happened again in 1968, but this time with glue. A scientist at 3M, Spencer Silver, was trying his best to create a super strong adhesive. Instead, he made a ridiculously weak one, a total failure. But years later, a colleague had this light bulb moment. He realized this failed glue was actually perfect for something else, making little bookmarks for his church hymnal that he could remove without tearing the pages. And just like that, the Post-it note was born from another happy accident. So, accidents aside, why are polymers so ridiculously versatile? I mean, how can one class of materials be used for everything from soft, cozy clothing to hard, rigid pipes? It really all comes down to design. The secret to all this versatility is the building block, the monomer. By making just a tiny, tiny tweak to that initial monomer, you get a completely different material. You start with one molecule, ethene, and you get flexible polyethene for things like plastic bottles. But swap that for a slightly different one, propene, and you create the tough fibers needed for carpets and ropes. Another small change gives you rigid PVC for pipes. It's like having a master key that you can cut in slightly different ways to unlock 1,000 different doors. It all goes back to the monomer.
But just choosing the monomer is only half the story. The other big trick is to link the chains to each other. This is called cross-linking. I want you to imagine all those long polymer chains just lying side by side, and then imagine adding rungs to turn them all into one big ladder. Well, those rungs lock everything into place, and that makes the material much more rigid and much stronger. This is exactly what Goodyear did with his rubber. He figured out how to build a molecular ladder.
And this one idea, cross-linking, it basically divides the entire world of plastic in two. On one side, you have thermoplastics, like a plastic bag. They have very few, if any, crosslinks, so the chains can just slide past each other. That's why you can melt them down and recycle them. But on the other side, you have thermoset polymers, like old-school bakelite. They are so heavily cross-linked that they're locked in place for good. Once they're made, they are set permanently. If you try to heat them, they won't melt, they'll just char and burn. This incredible ability we have to design materials has given us so many benefits, but it's also created this deep and really complicated paradox for our modern world. The benefits of the polymer age are, they're everywhere. We got materials that were both strong and lightweight, that were incredibly cheap and just endlessly versatile. They're chemically stable, which makes them perfect for everything from food packaging to medical devices. They even helped with conservation by giving us synthetic alternatives to natural materials like ivory. In short, polymers really gave us the blueprint for the convenient modern world we live in. But here's the paradox. Their greatest strengths are also their greatest flaws. That incredible durability means they just don't go away. They can stick around for centuries, accumulating in our oceans. And that chemical stability that makes them so useful, well, it also raises some serious concerns about the chemical additives locked inside them, and what happens when they finally do start to break down. These magic materials came with a hidden cost. So ultimately, the story of polymers is the story of a classic double-edged sword. The very materials that built the world of the 20th century have now become one of the greatest challenges for the 21st. And this leaves us looking towards the future. You see, our mastery of polymer science is only getting better. We're now designing biodegradable plastics and even self-healing polymers that can actually repair their own damage. We have more power than ever. So the fundamental question has changed. It's no longer just, what can we make? The real question is now, what should we make? What kind of world will we choose to build with these remarkable chains?